Hi, I'm Mark Law and I'm going to cover the second part of this tutorial on logic-based learning for interpretable AI. This part of the tutorial addresses logic-based learning of answer set programs. The first half an hour or so is going to focus on an introduction to logic-based learning under the answer set semantics. I'll start with a very brief overview of answer set programming, but I'm going to keep things very brief, so if you've never heard of ASP before, it might be best to go and watch a tutorial that introduces answer set programming a little bit more slowly. I'll cover the things that we need for the rest of this tutorial, so things like brave and cautious entailment, and then I'm going to move on to the initial approaches for learning answer set programs. So there are two forms of entailment in answer set programming called brave and cautious entailment that basically correspond to entailing things in either one answer set or in all answer sets of the program. And we'll see that actually early on, this led to two different kinds of inductive logic programming or logic-based machine learning called brave and cautious induction. And roughly speaking, what this meant was that we are either trying, in the case of brave induction, to cover all of the examples in at least one answer set of the program, or in cautious induction, we're trying to cover all of the examples in all answer sets of the learned program. So after that, I'm going to cover one of the algorithms for brave induction. This is called ASPAL. It was developed at Imperial College. And then after that, I'm going to discuss some of the limitations of brave and cautious induction. So specifically, you're going to see that there are some programs that can't be learned with either brave or cautious induction on their own. And that will lead us nicely on to my own learning framework called Learning from Answer Sets. Learning from Answer Sets actually combines aspects of both brave and cautious reasoning. And we've proved that it is actually resources allowing, it is able to learn any answer set program. Answer set programming is a declarative form of logic programming, and usually what we do is we take a problem that we're trying to solve, we encode it as a set of logical rules called an answer set program, and then the answer sets of this program, which are the solutions that we can find with any off-the-shelf ASP solver, are translatable into the solutions of the problem that we're trying to solve. So for instance, we could take a game like Sudoku, represent the rules of Sudoku as an answer set program, and then maybe put some constraints to say that certain numbers have to appear in certain places according to the numbers in a particular Sudoku grid that we're trying to solve. This then gives us an ASP program that we can solve using an off-the-shelf ASP solver. It will output a set of answer sets, and each of these answer sets then corresponds to one of the legal ways of filling in the numbers in that Sudoku grid. So just as a brief recap, I'm just going to cover the syntax that we'll be using in this tutorial. So on the slide you can see what's called a normal rule. The head of the rule is an atom. We've then got a set of literals in the body on the right hand side. These can be either positive or negative, where the negative literals represent negation as failure. Roughly speaking, what we mean by this rule is that if the body of the rule is satisfied, so if all of the B's are true, all of the C's are false, then the head must also be satisfied, so H must be true. In addition to normal rules, which are supported by other forms of logic programming such as Prolog, ASP also supports what are called choice rules. Now, the body of these rules is still the same as before, so it's still a conjunction of literals. It's the head of the rule that is slightly more complicated. And the big difference is that whereas a normal rule says that if the body of a rule is true, then the head must definitely be true, the body of the rule a choice rule allows us to say that if the body is satisfied, then there are a number of possibilities, so we get some kind of a choice. Now, more specifically here, we've got a lower bound, we've then got a set of atoms within the curly braces, and we've then got the upper bound. So what this actually says is if the body is satisfied, then at least the lower bound and at most the upper bound of the atoms in the head must be satisfied. So this gives us some kind of a choice, and in practice what this tends to do is generate multiple answer sets in which we get each of the different possible choices that are allowed by the lower bound and the upper bound. So choice rules allow us to generate multiple answer sets of a program. On the other hand, constraints allow us to eliminate undesirable answer sets of a program. So roughly speaking, the empty head of a constraint actually represents falsity, which means that if the body is satisfied, then falsity must be satisfied, which can't happen. And so what this constraint actually means is the body can never be satisfied in an answer set of the program. So this means we can't have the case where all of the B's are true and none of the C's are true. Effectively, this allows us to filter out some of the unwanted answer sets of our program. I'm not going to cover the formal semantics of answer set programming in this tutorial because it's out of the scope and you don't really need to understand it in order to understand the rest of the tutorial. All you need to know is that the answer sets of a program are a special subset of its Herbrand models. So a program might have one answer set, it might have multiple answer sets, or it might even have no answer sets. This actually leads to two different forms of entailment within ASP. So firstly, we say that an atom is bravely entailed by a program if it's true in at least one answer set of the program. And it's cautiously entailed if it's true in every answer set of the program. So if we consider a very simple ASP program here, we've got a choice rule with no body and a normal rule with no body, so that's called a fact. The choice rule says that at least one and at most one of the atoms P and Q have to be true in every answer set, and the fact says that R must be true in every answer set. So because of the choice rule, we're going to get two answer sets here, one containing P and R, and the other containing Q and R. And so what this means is that every atom is bravely entailed by the program because it occurs in at least one answer set of the program, and only the atom R is cautiously entailed. Because in general there are multiple answer sets of the ASP programs that we're trying to solve, and each of the answer sets corresponds to a perfectly valid solution of the problem that we're trying to solve, it's often very useful to express preferences over the answer sets. So this can mean saying that we want the cheapest solution, or rather the answer set corresponding to the cheapest solution, or some other metric to measure the quality of the returned solution. The way that we do this is by using what are called weak constraints. Weak constraints don't affect what is or is not an answer set of the program, but they simply put a preference ordering over the different answer sets. So I've given an example of a weak constraint on the slide. The body looks very similar to the normal rules and the choice rules that you've seen so far. So it can just be any conjunction of literals. In this case, it says that we've bought an item and the item costs M. What's different is that after the rule, we've actually got a tail to the rule. Now this is comprised of a few different elements. So firstly, the weight in this case is M, and what this means is that every time we satisfy this weak constraint, we're going to have to pay a penalty of M, and the priority level, which says roughly speaking how important this weak constraint is. And then finally, we've got a set of terms that appear after the weight and the priority level. Now, the importance of these terms is actually to specify which instances of the weak constraint we should consider as being unique. So if we see multiple instances of the same weak constraint being satisfied by an answer set, sometimes we want to consider those as violating the weak constraint multiple times, and sometimes we just want to count them once. And so what we do is that we put the terms in the tail of the weak constraint, and then it's actually only the unique tails which constitute different instances of the weak constraint when we're counting them. So more formally, what we're trying to do is to minimize the sum of the weights of the unique tails of weak constraints at each priority level. Now, higher priority levels are more important than low priority levels, and what I mean by that is that we first try to optimize or try to minimize the sum at the highest priority level, and then only if we have two answer sets that are equal at that priority level do we move down to the lower priority levels. So in a sense, the highest priority level is infinitely more important than any priority level beneath it. So just to give you an example of this, if we're trying to decide on different routes to get from one location to another, we might set up an answer set program such that each of the different answer sets corresponds to a valid route to get from one location to another. We can then put some preferences over these answer sets. So the first weak constraint on the slide corresponds to a preference that says that we want to avoid walking through areas with a high crime rating. And so every time that we do this, we want to pay a penalty of 1, and we'll end up minimizing the total number of times that we walk through an area with a high crime rating. The second weak constraint says that we want to minimize the number of buses that we have to take. And then finally, the lowest priority weak constraint says that we want to minimize the total walking distance of the journey. Now, this is slightly different to the two weak constraints above it because we're not paying a fixed penalty, and instead we're paying the penalty of the distance of that leg of the journey. And so what this means is that the total penalty that we pay at this priority level ends up being the total walking distance of the journey. And if we set up an answer set program in the way that I've described, so that each of the answer sets corresponds to one of the valid journeys that we could take, then we can use an ASP solver to order the journeys. And in this case, journey A is the best journey because we only we don't walk through any areas with a high crime rating. We only take one bus, and the total walking distance of the journey is only 400 meters. And so this is actually better than any of the other 3 journeys on the slide. Now that we've recapped the basic definitions for answer set programming, I'm going to cover the initial attempts at logic-based machine learning under the answer set semantics. So firstly, just to recap from the first part of the tutorial, when we're trying to learn definite logic programs, the basic setup for inductive logic programming or logic-based machine learning is that we've got a background knowledge that is a definite logic program, and then we've got a set of positive examples and a set of negative examples. Each of the examples here are atoms, and we're attempting to find a hypothesis such that for every one of the positive examples, the background knowledge union the hypothesis entails that example. And for every single one of the negative examples, the background knowledge union the hypothesis does not entail that negative example. Now, because there are 2 different well-established forms of entailment under the answer set semantics, when we try to translate this setting to the answer set semantics, we actually get 2 different forms of inductive logic programming. So firstly, I'm just going to cover cautious induction, which most of the very early approaches to learning under the answer set semantics adopted. And this sort of, roughly speaking, is the most similar to standard inductive logic programming, because in standard inductive logic programming, we're trying to entail it in the least Herbrand model, which corresponds to entailing in every model of the program. So here we're trying to entail in every answer set of the program. So we've still got a background knowledge. The only difference here is that it's an answer set program. We've still got positive and negative examples, and these are still atoms. And we're trying to find a hypothesis such that the background union the hypothesis has at least one answer set, so it's satisfiable. And for every answer set of the background knowledge union the hypothesis, every positive example is contained in that answer set, and each negative example is not contained in that answer set. So just to give an example, we've got a simple propositional background knowledge here, and we've got one positive example S and one negative example Q. So if we're trying to work out which of these four hypotheses are cautious inductive solutions, the first step would be to calculate the answer sets of the hypothesis union the background knowledge. And I've done this for us here. So the first one has two answer sets, the second one has no answer sets, and the last two have one answer set each. Now, the first hypothesis is not a cautious inductive solution, and that's because the second answer set contains the negative example Q, and so it's not the case that for all of the answer sets the negative example is not contained in the answer set. The second hypothesis is also not a cautious inductive solution, and that's because this hypothesis, when it's combined with the background knowledge, has no answer sets, and one of the conditions for cautious induction is that B union H must have at least one answer set. And then the next two are cautious inductive solutions. So they've only got a single answer set, and this single answer set in both cases contains the positive example and it doesn't contain the negative example. So these both satisfy both of the conditions for cautious inductions. They both have at least one answer set, and every one of their answer sets contains the positive example and does not contain the negative example. So although many of the early approaches to inductive logic programming under the answer set semantics did adopt cautious induction, there are some limitations with cautious induction. And this is because it's actually quite a strong condition to say that every answer set must cover all of the examples. And it means that it's very difficult to learn programs with multiple answer sets, and specifically programs with choice rules. So the program on the slide says that we've got a single coin, and for every coin that we've got, it either lands on heads or it lands on tails, and it doesn't land on both. If we were trying to learn this program, we need to give either positive examples, which occur in every answer set of the program, or negative examples, which occur in no answer sets of the program. Now, this program has two answer sets, one that contains coin of C1 and value C1 heads, and the other that contains coin of C1 and value C1 tails. So the only atom that we can give as a positive example is coin of C1, because the only other two atoms that occur in answer sets do not occur in both of the answer sets. And for a cautious induction example, it has to be something that is true in every answer set of the program. So we can give a positive example coin of C1, and then of the interesting atoms that occur in at least one answer set of the program, none of them, of the interesting atoms in the language of the program, I should say, none of them do not occur in any answer set of the program. So there's actually nothing interesting that we can give as a negative example when we're trying to learn this program. So the best we can do is just give a single positive example coin of C1, and actually, if we were to give that as an example to any sensible cautious induction system, it would have no incentive to learn the choice rule, because there are no examples for the value predicate. And so all it would end up doing is learning the fact coin of C1. This simple example actually represents or demonstrates a general problem with cautious induction approaches. They struggle to learn any rules which generate multiple answer sets, because they can only give examples of things that should be either true in every answer set or false in every answer set. So there's actually no incentive for any cautious induction system to learn programs with different answer sets. So you might think, well, cautious induction is too strong, and so the sensible thing to do would be to try the other form of entailment in ASP, which is slightly weaker, which is brave induction, or using brave entailment. So the Brave setting for ILP, it still has a background knowledge, which is an ASP program. It still has positive and negative examples that are atoms, and we're still trying to find a hypothesis. In this case, we're trying to find a hypothesis such that when we combine it with the background knowledge, it has at least one answer set that contains all of the positive examples and none of the negative examples. So this is a much weaker condition than for cautious induction. Now I'll go back to the example that I was showing before where we've got the same background knowledge and the same examples. We've still got the same answer sets, obviously, because I haven't changed any of the programs. Now in this case, we get a slightly different set of inductive solutions. So the first one now, it wasn't a cautious induction solution because it had at least one answer set that did not cover the examples, whereas for Brave induction, it's enough that it's got at least one answer set that does cover the examples. So the first answer set contains the positive example S and does not contain the negative example Q. And so this is a Brave inductive solution. The second hypothesis is still not an inductive solution because it has no answer sets. So obviously it's not the case that it has at least one answer set that covers the examples. And the third and fourth are still inductive solutions because they've both got at least one answer set that contains the positive example and doesn't contain the negative example. So there are actually quite a few implementations of Brave induction. Mostly these can be categorized into two types of system. So the first is based on Exhale, and I believe you've seen the Hale algorithm as part of the first half of this tutorial that Alessandra covered. Exhale is an extension of the Hale algorithm, and it's led to a few further extensions developed by other authors. So the ILED system and the Inspire system are both based on the Exhale system. And then secondly, the Aspal system. I'm going to cover Aspal in the next few slides. Aspal encodes a Brave inductive task as an answer set program, such that then the answer sets of this program correspond to all of the Brave inductive solutions of the task. It's also inspired an extension called Raspal that I'm not going to have time to cover in this tutorial. One of the fundamental concepts of the Aspal system is what are called skeleton rules. So the first step actually of the Aspal algorithm is to compute a set of rule templates that represent the hypothesis space. And by rule template, what I mean is that the constant placeholders have not been actually instantiated with any constants. So mode declarations in Aspal are actually very similar to what are available in other ILP systems and what you'll have seen in the first part of this tutorial. So they just specify what should occur in the head of the rule and what can occur in the body of a rule, and the arguments are placeholders for either variables or constants. We still have this notion of input and output variables that you've seen in the first part of the tutorial. So given the mode declarations on the slide, one valid skeleton rule is the rule that says that V1 is a penguin if V1 is a bird and V1 can't do the ability C1. So C1 actually comes from a constant placeholder for ability, but because this is a skeleton rule and not actually a rule that appears in a hypothesis, C1 has not yet been instantiated with an actual constant. So there are two rules given the background knowledge and the two abilities that we have, fly and swim. There are two rules that this skeleton rule could actually represent. So either it says that V1 is a penguin if it's a bird that can't fly, or it can say that V1 is a penguin if it's a bird that can't swim. When we're computing these skeleton rules, we have a few hyperparameters which specify a few constraints on the kinds of rules that we can generate. So Lmax just means the maximum number of literals that are allowed to appear in the body, and Vmax is the maximum number of variables. if we use if we set Lmax to be 2 and Vmax to be 1, then given these mode declarations and this background knowledge, we get 3 skeleton rules. So firstly, that V1 is a penguin if it's a bird, V1 is a penguin if it's a bird that can't do C1, and V1 is a penguin if it's a bird that can't do C2. Now notice that although Lmax is 2 here, the final rule does actually have 3 body literals, and that's because when we count the number of body literals, we don't count the atoms that are only there to specify the types. So bird doesn't actually come from a mode declaration on its own, it's only there because we've introduced a variable v1 of type bird. So we don't actually count this when we're computing either the number of body literals in the rule or the length of the rules in the hypothesis. Once Aspal has computed the full set of skeleton rules, the next step is to encode the search for an inductive solution as an answer set program. This encoding relies on a mapping between skeleton rules and meta-level atoms within the ASP program. Each skeleton rule is represented as a meta-level atom with the predicate rule and the first argument being an identifier for the skeleton rule. So this is just usually an index, and then the rest of the atoms are the variables representing constant placeholders in the skeleton rule. So for instance, if we take a skeleton rule that says P of V1, V2, if Q of V1, C1, and R of V2, C2, and this has got identifier 2, then this skeleton rule is represented by an atom rule of 2, C1, C2. And so if we take a ground instance of this atom, rule of 2, AB, then this represents the skeleton rule where C1 has been replaced by A and C2 has been replaced by B. We'll now go back to the penguin example where we've got a background knowledge that says that we've got 2 birds, A and B, 2 abilities, fly and swim, and we know that A can fly and B can swim. We've already computed the skeleton rules for a set of mode declarations, and these are given between lines 14 and line 16. And we've got one positive example that says that B is a penguin, and one negative example saying that A is not a penguin. We can encode this as an answer set program and use the answer set program to search for the brave inductive solutions. And this is actually exactly what Aspal does. So firstly, if we just put the background knowledge straight in, and then for the skeleton rules, what we're going to do, we're going to add them, but we're also going to add to the body of the rule the meta-level atom representing that rule. So we'll give the first skeleton rule an ID of 1. It doesn't have any constant placeholders, so 1 is its only argument. For the second rule, we're going to add C1 because that has a single constant placeholder C1. And then for the third rule, we get rule 3 C1 C2 because that has 2 constant placeholders. Next, for the examples, what we need to do is we need to add a constraint that says we've got to prove the positive example and we can't prove the negative example. So we write this as, in Aspal anyway, we write this as the goal is to prove penguin of B and not prove penguin of A. And then we put in a constraint that says it can't be the case that we haven't proved the goal. And then finally, we need to put in a choice rule that says which rules we're allowed to learn. So in Aspal, the way that we do this is we just put a choice rule saying that we're allowed to abduce, effectively, rule 1. We're also allowed to abduce rule 2 of C1 for any ability C1. and we're also allowed to abduce rule 3, C1, C2 for any pair of abilities C1 and C2. Okay, so the empty lower bound and upper bound here says that we can actually abduce any number of these rule atoms. If I run this in Klingo and tell Klingo to search for all of the answer sets, then we get quite a lot of answer sets here. So there are 12 answer sets. What I'm going to do is put in a show statement that just says that we're only interested in the rule atoms. So that's rule with arity 1, 2, and 3, just to make things a little bit easier for us. And so you can see we've got lots of answer sets. So for instance, answer set 5 here says that if we abduce the rule 2 fly, then we're able to prove the positive example and not prove the negative example. Okay, so that would be the rule that says if V1 is a penguin and V1 can't fly, sorry, if V1 is a bird and V1 can't fly, then V1 is a penguin. And this actually corresponds to the definition that we're trying to learn. But you'll notice that there are lots of other solutions here. So for instance, once we put in that rule, if we put in lots of the other rule 3 atoms, then we're also able to still prove the positive example and not prove the negative example. Now, in ILP, what we tend to do is we put a preference ordering over the hypotheses. So I've already shown you that there is a construct in answer set programming for putting preference orderings over the answer sets, and these are weak constraints. And so what we can do is we actually say for any rule that we learn, we're going to pay a penalty of the length of that rule. So for instance, if we learn rule 1, then we're going to pay a penalty of 1 at priority level 1. Rule 2, for any constant placeholder C1, we're going to pay a penalty of 2 because this has 2 literals if we don't include the type atom bird of V1. And here notice that I'm putting C1 in the terms because if we learn multiple definitions using rule 2, then we want to pay for each of them. And then we'll have rule of 3, C1, C2. Wrong penalty there. That should be 3 because this has 3 literals. And you can see now the optimal solution is rule of 2 fly. So this is actually the shortest possible solution for covering all of the examples. Now this is an approach to brave induction, and in this case, because there's only one answer set of each of the programs, so for each hypothesis that we can construct with this, when we combine it with the background knowledge, it only has a single answer set. The notions of brave and cautious induction coincide here. But if, for instance, I were to say that now we're not sure whether A can fly, so either it can fly or it can't fly, and I make that a choice rule, then you can see that we're still getting the solution rule 2 fly, even though in only one of the answer sets we'll cover the examples. And so this shows that Aspal in fact only finds brave inductive solutions of any given learning task. So we've seen brave induction now, and we've also seen an algorithm that is able to compute the brave inductive solutions of any brave induction task. You might be wondering whether this solves all of the problems that we had with cautious induction. So I said that cautious induction is not able to learn some answer set programs, and that was the motivation for considering a slightly weaker form of induction in brave induction. So if we consider a learning task now with a background knowledge that says that any coin must land on either heads or tails, and not both, and we've got a single coin C1 that we know is what's called a biased coin. This program has two answer sets, one where the coin lands on heads and the other where the coin lands on tails. We might be in a situation where we want to learn a constraint that eliminates one of those answer sets. So here, this constraint that we're trying to learn says that any coin that is biased cannot land on heads. In order to do that, we have to give examples under Brave induction of things that occur in at least one answer set, or for negative examples, things that don't occur in that answer set. Now, there's only one answer set remaining of the target program, so the background knowledge combined with this constraint. It just has an answer set that contains value C1 tails, coin of C1, and biased coin of C1. So we can give all of those three things as positive examples and give as many negative examples as we like. So really the only interesting one would be value C1 heads. But although the target program would cover all of those examples, the background knowledge on its own already has an answer set that covers all of those examples. And so actually any sensible Brave induction system would have no incentive to learn the constraint, because any constraint only eliminates some of the answer sets. And so if the constraint combined with the background knowledge covers the examples, then the background knowledge on its own is already guaranteed to cover all of the examples. And so returning the empty hypothesis is going to be the optimal inductive solution in this case. So actually this is a general property of Brave induction systems. It's impossible with any Brave induction system to learn constraints. So far I've shown you that there were two leading approaches to inductive logic programming under the answer set semantics, Brave and cautious induction, and they both have their weaknesses when it comes to learning general answer set programs. So Brave induction can't learn constraints, and cautious induction, roughly speaking, can't learn choice rules. And this was the motivation for the beginning of my research into learning answer set programs. And I came up with a general framework for learning answer set programs called Learning from Answer Sets. So I've already covered answer set programming in my brief recap earlier. And if you recall, when we're using answer set programming, we're trying to solve a real-world problem by encoding it as a set of logical rules called an answer set program. We then find the answer sets, and these correspond to the solutions of the problem that we're trying to solve. With learning from answer sets, what we actually do is we reverse this process. So we take examples of solutions, we encode these as examples of what should or should not be an answer set, or actually a partial answer set in the case of learning from answer sets. And then we try to learn an answer set program that corresponds to the rules of the real-world problem that we're trying to solve. So for instance, we can give examples of what should or should not be a valid Sudoku board and learn the rules that correspond to the rules of Sudoku. Examples in learning from answer sets are what's called partial interpretations. So they're much more complicated actually than the atomic examples that you've seen so far, in that each example now is a pair of sets of atoms called the inclusions and the exclusions. We say that an interpretation extends a partial interpretation if it includes all of the inclusions and doesn't include any of the exclusions. So just to give a simple example here, we've got a partial interpretation on the right-hand side of the slide with P and Q as the inclusions and R as the only exclusion. The two interpretations on the left-hand side do extend this partial interpretation because they both contain both P and Q, and neither of them contains R. If we take these two interpretations, though, they do not extend the partial interpretation. The first interpretation, containing only P, does not extend the partial interpretation because it doesn't contain Q, which is one of the inclusions. And the second one does not extend the partial interpretation because it contains R, and R is an exclusion. Now that I've introduced the form of the examples in learning from answer sets, I can give the formal definition of the learning framework. So similarly to the other two frameworks for learning under the answer set semantics, we still have a background knowledge, which is still an ASP program. We have a set of positive and negative examples that are partial interpretations. So this is different to the other two forms of logic-based learning under the answer set semantics. We still have a hypothesis space. In this case, it's a set of normal rules, choice rules, and constraints. And we're aiming to find a hypothesis that's a subset of this hypothesis space, such that for each of the positive examples, there is at least one answer set that extends that positive example. And for each of the negative examples, there is no answer set that extends that negative example. So notice actually that for each positive example, it can be a different answer set extending it. So we can say, for instance, there is one answer set that contains heads and another answer set that does not contain heads. And that's fine. So long as there exists an answer set that contains heads and another answer set that doesn't, we'll have covered both examples. For the negative examples, it's a much stronger condition because we're saying there is no answer set that extends the partial interpretation. So this actually can equivalently represent that all answer sets should satisfy a condition, which is basically the negation of the partial interpretation. So how does this relate to the other two forms of inductive logic programming? Well, firstly, for brave induction, we can encode this as a learning from answer sets task with a single partial interpretation example. So we take the original positive examples, and these become the inclusions of the partial interpretation, and the negative examples become the exclusions of the partial interpretation. We have no negative examples in the learning from answer sets task, and what this now says is that any hypothesis that's an inductive solution of this task must extend that partial interpretation. So it must contain all of the inclusions, so all of the original positive examples, and none of the exclusions, so none of the original negative examples. And this is exactly the same as the condition for brave induction, which says that there should be at least one answer set that contains all of the positive examples and none of the negative examples. So if we take the example brave induction task that we had before, we can represent this as a learning from answer sets task with a single partial interpretation, with one inclusion S and one exclusion Q, and we've got no negative examples here. For cautious induction, the translation is slightly more complicated. So in cautious induction, each positive example must occur in every answer set of the learned program. So this condition of all answer sets must contain the atom is actually equivalent to saying that no answer set cannot contain the atom. And we can represent this in learning from answer sets with a negative example. So each of the positive examples is transformed into a negative example with no inclusions and a single exclusion, which is the positive example. So for instance, the first negative example in the learning from answer sets task here says that there can be no answer set of B union H that does not contain E plus 1, which is equivalent to saying that every answer set must contain E plus 1. For the negative examples of the cautious induction task, we again transform these into negative examples in the learning from answer sets task. So for instance, we say there should be no answer set that contains E minus 1, and this is equivalent to the condition for cautious induction. In addition to these negative examples, we must also have a single positive example. This positive example is empty, so no inclusions and no exclusions, and all this says is that there should be at least one answer set of the learned program, because this is one of the conditions of cautious induction. So for example, if we take the example task that I was showing earlier in the talk, we can transform this into an equivalent learning from answer sets task. We've got a single positive example that just says that there should be at least one answer set, and we've got two negative examples. The first one says there should be no answer set that does not contain S, which is equivalent to saying that every answer set should contain S. And the second one says that there should be no answer set that contains Q. And so this reflects the negative example in the cautious induction task. So in this tutorial so far, I've covered a brief recap of ASP. We've also covered brave and cautious induction and their limitations. We've covered the ASPAL algorithm and learning from answer sets, which is able to combine aspects of both brave and cautious induction, and in fact is actually capable of learning any answer set program up to strong equivalence. In the next part of this tutorial, I'm going to cover the original versions of ILASP, so this is ILASP 1, 2 and 2i, context-dependent examples, and preference learning. So the latter two, the context-dependent examples and the preference learning, require extensions of the basic learning from answer sets framework that I've just shown you. So firstly, I'm going to go through the ILASP algorithms, and I'm going to show why ILASP 1 and ILASP 2 are a bit slow, which was the original motivation for the iterative version of ILASP, ILASP 2i. And then I'm going to show you context-dependent examples, which allow us to give an extra bit of background knowledge with each example that only applies to that example. And I'm going to show that that actually allows for a much more natural representation of some learning tasks under the answer set semantics. And then finally, in this part of the tutorial, I'm going to show you preference learning. So this is how we learn weak constraints, and we could do this with some extra kinds of examples called ordering examples within learning from answer sets. And this leads us to a more general notion of the learning from answer sets framework called context-dependent learning from ordered answer sets. So the basic ILASP algorithm, or the first ILASP algorithm, ILASP 1, relies on a fundamental set of concepts called positive solutions, violating solutions, and inductive solutions. So I've already introduced to you what it means for something to be an inductive solution. That means all of the positive examples have to be covered and none of the negative examples can be extended by any answer set of the learned program. And by this I mean that all of the negative examples have to be covered. So for a hypothesis to be a positive solution, it has to be the case that it covers all of the positive examples, but we don't have to guarantee anything about any of the negative examples. A violating solution, then, is a hypothesis that covers all of the positive examples and doesn't cover at least one of the negative examples. So there's at least one negative example that is extended by one of the answer sets of B union H. So then the inductive solutions of the task are exactly those positive solutions which are not violating solutions. What this means is that at each length n, the positive solutions that are not violating solutions are the inductive solutions of length n. And so we can start at n equals 0 and keep computing the positive solutions that are not violating solutions. And as soon as we get to a point where at length n the positive solutions that are not violating solutions are non-empty, then this set of solutions is guaranteed to be the set of optimal solutions of the whole task. And this is exactly what ILASP 1 does. So it starts at length 0 and keeps incrementing n until it finds a non-empty set of inductive solutions. It does this by first computing the set of violating solutions, using a similar meta-level ASP approach to that used by ASPAL, converts these violating solutions into constraints and adds them back into the meta-level program, runs the meta-level program again in ASP, and this gives it the set of positive solutions that are not violating. So I can show an example of this. This is an example learning task where we're trying to learn the rules of Sudoku. In the background knowledge, we've just got the definition of the grid, so the cells that appear in a 4x4 grid, the blocks that appear in that grid, and then what it means for two cells to be in the same row, column, or block. We've got a positive example, and this says that the first row is 1, 2, 3, 4. The second row, the third element of it is a 2, and in the exclusions, we're just saying that the first cell is not a 2, 3, or a 4. So this is a partial interpretation, and so there are some cells that are completely unspecified in this example. We've then got 3 negative examples corresponding to the 3 constraints that say that we can't have 2 cells in the same row, column, or block that share the same value. And so these 3 negative examples are just instances of these 3 constraints. If I run this in ILASP1, it's going to take a very long time, and that's because it's going to have to find all of the violating solutions at each length up to the length of the first inductive solution, which is actually of length 17. So it's going to find a very large number of violating solutions. I think it's actually 14 million violating solutions, and then it will return the first inductive solution. Now, I've already used ILASP to compute an ASP program, construct an ASP program that is equivalent to running ILASP1. This is in the file meta-t, so you can use ILASP to actually output this program. I'm going to run this in Klingo. Because it's a very old version of ILASP, it needs an old version of Klingo, which is why I'm running Klingo 4.3. And you can see it's going solving before it finds any solutions at all. That's because up to a certain length, there are actually no positive solutions, and so all of those solve calls return nothing. You can see that then it finds a very large number of solutions at each length. These are all of the violating solutions. It's converting those into constraints and then solving again, and it finds no solutions that are not inductive solutions, that are inductive solutions, and so it's incrementing the length and solving again and finding another set of violating solutions. So I'm going to leave that running for a while, and then when we come back, you'll see that it will have found the inductive solution. Okay, so the task is finished running now, and it's taken well over 15 minutes to complete, but this has found the inductive solution, or at least these atoms correspond to the inductive solution. Now, this took a very long time because of the number of violating solutions that needed to be computed, and this was the motivation actually for ILASP2, the fact that you can get some very small learning tasks in ILASP1 that take a very long time to complete, because ILASP1 doesn't handle negative examples very efficiently. And so the big change with ILASP2 is that instead of computing a single constraint per violating solution, we instead try and find an optimal violating solution in every iteration, and then find a reason for that solution being violating. So we can then translate that reason into a set of constraints that rule out not only that particular violating solution, but also all other violating solutions that share the same reason. So I'm going to run ILASP2 now on the Sudoku task. And you can see it runs in around 2 seconds. Now I'm going to run this in a slightly different mode now, where you can see that a similar output from Klingo. So what this does is it constructs the program that's being sent to Klingo, and instead just outputs it. So I'm then piping that to Klingo so that we can see all of the output. So you can see things are happening fairly quickly. I'm running with a few different parameters actually, so this is going to take a little bit longer than the task when ILASP runs it, because it runs it with a few different parameters for Klingo. So you can see it's found a similar inductive solution. I think it's actually the same one as was found by ILASP1, but there were only 9 calls to Klingo, which means actually that it only needed 8 violating reasons in order to extend the constraints enough so that the solution on the 9th call was an inductive solution, and in fact the optimal inductive solution. And this is why ILASP2 is much, much faster than ILASP1 on tasks with negative examples. Although ILASP2 is much faster than ILASP1 on some tasks, specifically those with negative examples, ILASP2 still shares one of the scalability issues of ILASP1, which is that when there are large numbers of examples, both systems run very, very slowly. And this is because they both encode the task using a meta-level ASP representation whose grounding is proportional to the number of examples in the task. So the more examples you have, the larger the grounding, and the larger the grounding in ASP, the longer the program will take to solve. So although ILASP2 does address some of the scalability issues, it's by no means a scalable system with respect to the number of examples. So what we did to address this was we introduced ILASP2i, which works using what are called relevant examples. The idea here is that in many real tasks, lots of the examples will actually be explained by exactly the same hypotheses. So in a sense, there are kind of equivalence classes of examples, and we only need to consider one example from each equivalence class in order to actually find the right hypothesis. So the way that we construct these, or rather this set of relevant examples, is to use an iterative approach where we pick a seed example each time that is not covered and add it to the set of relevant examples. This is similar to the idea of a cover loop in other ILP systems, but there are a few differences. So in a cover loop, what you tend to do is you iteratively learn a hypothesis rather than iteratively constructing a set of examples. So you pick a seed example, and then you extend the hypothesis that you got to last time with some additional rules. And that works in traditional ILP because they're only focused on learning definite logic programs. So they're monotonic, meaning that as you add things to the program, you're guaranteed to still cover the examples that you covered last time. When we're learning non-monotonic programs, such as answer set programs, this approach wouldn't work. So instead, what we do is we iteratively build a relevant subset of the examples, and in each iteration, when we do the learning, we start from scratch. So we don't build on the hypothesis that we learned last time, we just try to find the optimal solution with respect to the relevant subset of the examples. But because we're starting from scratch, we also need to keep track of all of the previous relevant examples, whereas in the cover loop approaches, they don't need to worry about examples that are already covered. So more formally, this is the ILASP2i procedure. We've got the input task, and we start with an empty set of relevant examples. This is written as a pair so that we've got the relevant positive and the relevant negative examples. In the first iteration, the hypothesis is guaranteed to be empty because the optimal solution to an empty set of examples is always going to be the empty program. We then try to find a relevant example. This is one that is not covered by the empty hypothesis. If there is such a relevant example, then we enter the while loop. We add the relevant example to the relevant example sets. So if it's positive, it gets added to the first element of the pair, and if it's negative, it gets added to the second element of the pair. We then call ILASP2 on the learning task using only the relevant examples. If there is a solution to the task, then we just try to find another relevant example with respect to our new hypothesis, and then we go around again. If there is no inductive solution for the set of relevant examples, then we know that the whole task must be unsatisfiable too, and so we return unsatisfiable. Eventually, we'll get to a point where there is no relevant example for our given hypothesis. And so at this point, we know that H is an inductive solution of the whole task. We also know that it's an optimal inductive solution of the task with only the relevant examples, and so it must also be an optimal solution of the full task. So when we return it, we know that ILASP2I is finding a globally optimal solution, even though at each point when it's been searching for a hypothesis, it's only been considering the relevant subset of the examples. So just to give an example of this, say we've got a background knowledge with the successor relation, so 2 is the successor of 1, and so on. We've got examples of a less than predicate. Okay, so each example is a partial interpretation with only one inclusion, and we're saying that A is less than B, and giving it as a positive example if A actually is less than B, and giving it as a negative example otherwise. We've got some mode declarations specifying what we're allowed to learn, so we're allowed to use the less than predicate in both the head and the body, and we're allowed to use the successor relation in the body, and we're only allowed to use these positively, just to keep things simple. So we start off in ILASP2I with an empty set of relevant examples and an empty hypothesis. And then we try to find a relevant example, so that's one that isn't covered by the empty hypothesis. So here the easiest thing we can do is just pick 1 is less than 2. That's a positive example, but it's not explained by the empty hypothesis. We then use ILASP2 to find the optimal solution with respect to this single example, and we just get that x is less than y if x is the successor of y. That's the shortest safe rule that explains that example. But clearly it doesn't cover all of the examples, so we can add another example, which is that 1 is less than 4. That isn't explained by the current hypothesis, so we can add that to the relevant example set. We then use ILASP2 to update our hypothesis, well, to find a new hypothesis to replace it, rather. And we get that x is less than y if x is the successor of z, where z is some other integer, so it's the successor of at least one number, and y is also the successor of at least one other number. So obviously that covers the 2 positive examples that we have, but it doesn't cover all examples still. So we can add another example, this time a negative example. So 2 is not less than 1, so we can give this as a negative example, and it's a relevant example because our previous hypothesis didn't cover it. It proves that 2 is less than 1 where it shouldn't. We then use ILASP2 again to learn a new hypothesis, and we get that x is less than y if x is the successor of z and z is less than y, and x is also less than y if x is the successor of y. So this is actually the correct definition, and so there are no further relevant examples. And even though we had many thousands of examples in the full task, we only needed 3 relevant examples in order to find the correct inductive solution. Before we move on, I just want to quickly show an example of ILASP2I running on a real task. This is an agent planning problem where ILASP is attempting to learn the rules behind how an agent is allowed to move in the grid. I'm going to show this in more detail later when I show some applications of ILASP. But this is just an example of a learning task with over 200 examples. And ILASP2I is going to run on this, and it will need a very small number of these examples in order to actually find the optimal inductive solution. So I'll start ILASP running now. You can see it's, first of all, it chooses the empty hypothesis, it finds a counterexample, and then it learns a hypothesis to cover that counterexample. Counterexample here is used interchangeably with relevant examples, as I was using in the slide. And you can see after only 3 iterations, and 17 seconds, it's able to find the correct inductive solution. So although there are 200 examples in the full learning task, it only needs 3 of them to find the correct inductive solution. Okay, so now you've seen ILASP 1, 2 and 2I working on some learning from answer sets tasks, and this was the fundamental learning from answer sets framework. Since Learning from Answer Sets was published back in 2014, we've extended it in a number of ways, and I want to go through some of those extensions in the tutorial today. So the first is with a notion of context-dependent examples. Now, the motivation for this is that when we're actually solving an answer set program, usually we don't just solve a fixed answer set program for each problem. What we tend to do is we'll have a general set of rules, and then when we're solving a particular problem instance, we'll add some context to the set of rules. So effectively, that's an input that we're trying to solve. So for instance, say we've got a general set of rules defining what it means for a graph to be Hamiltonian. We can add a set of facts defining a particular graph. So that's what I've done here with the input context at the bottom of the slide, where we say what nodes are in that graph, what edges are in the graph, and then when we solve the program together, so the general rules together with the context, we'll get a set of answer sets. And so in this case, if there are any answer sets, then we know that the graph has Hamilton cycles, so it is Hamiltonian. If we change the context, then we get different behavior. So here, when I input a different graph or a different representation of a graph, then I get unsatisfiable from the answer set solver because actually this graph is not Hamiltonian. But I'll keep a fixed set of rules and I might run it with lots of different contexts depending on the problem instance that I want to solve. And this really was the motivation for context-dependent examples. We might have examples of different problem instances and want to give them together with different contexts. So in addition to the partial interpretation, we can also now give this extra element, e-context, which is an ASP program. And this is an ASP program containing usually just facts, if we're using it in the way that I described in the previous slide, but it can in principle also contain constraints and choice rules, so anything really that's definable within ILASP. Given a program and an interpretation, we say that I is an accepting answer set of a context-dependent partial interpretation if I is an answer set of the program P combined with the context, and I extends the partial interpretation. The way that we use this in context-dependent learning from answer sets is that the program P will be our background knowledge union the hypothesis. And so now, rather than the fixed program B union H having to cover the example, it's B union H union this example-specific context that has to cover a particular example. So just to give some examples of context-dependent partial interpretations, say we've got a program P which is P if not Q, and we've got an interpretation containing only P. This is an accepting answer set of the context-dependent partial interpretation in the first bullet point. So this says that we've got an empty context. We add this to the program, and so we're left with just P because the context is empty. This has one answer set containing only P, so it is an answer set, and it's an accepting answer set because it extends the partial interpretation. The empty interpretation is not an accepting answer set because it's not an answer set of the program union in the context. P, or the interpretation containing only P, is not an accepting answer set of this context-dependent partial interpretation because this only has one answer set when you combine Q with the program P, and this contains only Q. So there's no answer set containing only P. If we give instead the interpretation Q, then this is an accepting answer set because it's an answer set of the fact Q union the program P, and it does not contain P, so it extends the partial interpretation. We can now extend learning from answer sets with this notion of context-dependent partial interpretations. So our positive and negative examples become CDPIs now. Our hypothesis space is still the same, and we're now looking for a hypothesis such that each positive example has at least one accepting answer set, with respect to B union H, and each negative example has no accepting answer sets with respect to B union H. So in the positive example case, that means that there should be at least one answer set of B union H union the example context that extends the example partial interpretation. So just to give a very simple example now, we've got two context-dependent examples. One that says in the empty context, we should have at least one answer set that contains go out. And in the context where it's raining, we should have at least one answer set that does not contain go out. So one solution to this is that we learn the rule go out if it's not raining. So this covers both examples. Context-dependent examples are very good at expressing learning tasks which are naturally context-dependent. So for instance here we've used the weather conditions. But in addition to that, they can also be used to actually partition the background knowledge in tasks that do not at first glance appear to be context-dependent. So for instance here, we're representing a learning task where we're trying to learn what it means for a graph to be Hamiltonian. So in this case, we've got a background knowledge that defines the set of all possible graphs. So this just says the size has to be an integer between 1 and 4, and given a particular size, we get that number of nodes, and for each pair of nodes in the graph, we can either have an edge there or no edge there. So we can give examples of partial interpretations where we specify the size and the edges in the graph, and then we can learn the correct definition of what it means for a graph to be Hamiltonian. But this can also be partitioned into a context-dependent task. So what I mean by that is that the background knowledge can effectively be split into all of the different contexts that represent the actual graphs. So rather than having a background knowledge that actually defines all of the graphs, instead of that, we just give in each example the actual nodes that appear in that graph and the edges that appear in that graph, and an empty partial interpretation. And this is in fact equivalent to the previous learning task, but it's actually a bit more natural as well, because in the previous learning task we had to give the definition of all of the graphs up to a particular size. Now if we have another graph that comes along that's actually of a larger size, so for instance here we say all graphs up to size 4, and then we see an example later on of a graph of size 5, we have to redefine the background knowledge in order to cope with that example. Whereas in this case, we just specify that there are 5 nodes in the context, and we don't have to change anything about the rest of the task. So it's a more general way of defining a learning task. In addition to being a slightly more natural way of encoding some things, it's actually also a lot more efficient. ILASP2I with context-dependent examples can actually be many orders of magnitude faster than ILASP2I with non-context-dependent examples. The second extension that I want to cover to do with learning from answer sets is a notion of logic-based learning of preferences. So if you've taken other machine learning courses, you might have come across notions of preference learning before, so there are actually several different approaches. Collaborative filtering approaches usually identify similar users, and one user has recommended items based on the actions of other users. So for instance, I might say to you, students who have taken courses like these courses also took knowledge representation, so you might be interested in taking knowledge representation. So this quite often happens when you buy an item on Amazon, for instance. You'll get people who bought this also bought such and such, and try and rope you into buying even more stuff from them. There are other approaches, known as object ranking approaches, where instead of trying to classify similar users, what we're trying to do is learn an ordering over a set of objects based on examples of which objects are preferred to other objects. So for instance, I might witness that you prefer one journey over another journey, and then based on that, learn some preferences and use that to recommend different journeys to you in the future. This is quite natural to do in ASP, so in ASP objects are represented by answer sets, and preference orderings are represented by the optimization orderings of the answer sets. We've already seen that weak constraints can be used to create preference orderings in ASP. So I've shown you this journey preference example where we can encode our preferences as a set of weak constraints and use an off-the-shelf ASP solver in order to order a set of journeys or even find the best journey out of a set. We want to do this in reverse though. We don't want to give the preferences up front. What we want to do is give a set of examples of the orderings of the answer sets, and from that learn the set of weak constraints. So a context-dependent ordering example for us is just a pair of context-dependent partial interpretations, and roughly speaking what we're saying is that the first partial interpretation, or context-dependent partial interpretation, should be preferred to the second. Now, similarly to in ASP with entailment, there are two notions of coverage for ordering examples, and these are brave and cautious. We say that an ordering example is bravely respected if there's at least one pair of accepting answer sets of the two examples, such that the first answer set is preferred to the second answer set. We then say that it is cautiously respected if every such pair of accepting answer sets is ordered such that the first answer set is preferred to the second answer set. So now we can define the extended version of the learning task. This is now called context-dependent learning from ordered answer sets, rather than just learning from answer sets. And in this learning task, we've got a background knowledge. We've got positive and negative examples that are still context-dependent partial interpretations. We've got brave and cautious ordering examples that are now context-dependent ordering examples. The hypothesis space can contain normal rules, choice rules, and both hard and weak constraints. And the goal is to find a hypothesis that covers all of the positive and negative examples in the same way as before, bravely respects all of the brave orderings, and cautiously respects all of the cautious orderings. So in this part of the course, I have covered relevant examples. I've covered ILASP1, ILASP2, and ILASP2I, context-dependent examples, and preference learning. So in the next part, what I want to discuss is the generality of the different learning frameworks. So I've shown you lots of different approaches to logic-based learning under the answer set semantics, and I've given you some examples of programs that can and cannot be learned by different learning frameworks. So for instance, brave induction is incapable of learning constraints. What I want to do here is give a bit more of the formal background on why particular learning frameworks can't learn certain things. So as I just said, several learning frameworks have been proposed for learning ASP, and we've seen that some of them can't learn simple ASP programs. So now what we're going to consider is how we can formalize this and how we can capture exactly what programs can be learned by each learning framework, and therefore by each system that implements each of these learning frameworks. And also, we're going to consider the other side of the coin, so whether certain learning frameworks have tasks that are computationally harder than other learning frameworks. So what penalty do you pay for this increased generality of being able to learn additional classes of program? So the intuition behind the way that we're going to model this is with a new notion called distinguishability. So if we consider we've got a background knowledge that's just a standard ASP program, so a loop P if not Q, Q if not P. So this has two answer sets, one containing P and one containing Q. And we're trying to learn the hypothesis, which is a constraint saying that we don't want P to be true. We've seen already that brave induction wouldn't be able to learn this. And this is because there are no examples that can distinguish this constraint from the empty program. So we've seen previously that whatever examples we give to learn this constraint, even if we allow the constraint to be an inductive solution of the task with these examples, then the empty hypothesis would also be a solution of the learning task. And so this is what I mean by we can't give examples to distinguish this program from the empty program. But it is capable of doing it the other way around, actually. I can distinguish, or rather Brave induction can distinguish, the empty program from the constraint, because we can give a positive example, P, right? And so the empty program would cover this, whereas the constraint would rule out the only answer set that contains P, and so it would not cover that positive example. More formally, we say that a learning framework is capable of distinguishing one hypothesis from another with respect to a given background knowledge if there's at least one learning task in that framework with the given background knowledge and any set of examples that we care to choose, such that the first hypothesis is a solution or an inductive solution given that framework, and the second hypothesis is not an inductive solution. We can then compute what we call the one-to-one distinguishability class, which is basically the set of all tuples containing the background knowledge and these two hypotheses, such that the learning framework can distinguish the first hypothesis from the second with respect to that background knowledge. So if we consider a simple task now where we're trying to learn the hypothesis P, and we've got a second hypothesis which is a choice rule, saying that P could either be true or false, then with the empty background knowledge, B, H1, H2 is not in the one-to-one distinguishability task for Brave induction. The reason for this is that the best examples we can give to learn the fact P is just the positive example P and no negative examples, and if we give these examples, then H2 is also an inductive solution of the task. However, if we flip these round, then B, H2, H1 is in the one-to-one distinguishability class, and that's because we can give the examples with an empty set of positive examples and just P as a negative example, and the second hypothesis does cover this set of examples because it has an answer set that doesn't contain P, whereas the first hypothesis does not cover this set of examples because its only answer set, when combined with the background knowledge, contains P. And this will change between the learning frameworks. So something that is in the distinguishability class, or the one-to-one distinguishability class for Brave induction might not be for cautious induction, or the other way around. So for instance, if we take B, H1, H2, this is in the one-to-one distinguishability class for cautious induction, because we can give the positive example P, and this now says that every answer set must contain P. And so H1 is an inductive solution of this task, whereas H2 is not an inductive solution of this task. And so H1 is distinguishable from H2. The table on the slide shows sufficient and necessary conditions for a tuple to be in the one-to-one distinguishability class for each of the learning frameworks that we've discussed. So you can see that for this to be the case for Brave induction, it has to be the case that B union H1 has at least one answer set that is not contained in the answer sets of B union H2. Once we've done this, we can actually reason about the different sizes of the distinguishability classes of each of the frameworks. So we can see that both Brave and cautious induction have strictly smaller one-to-one distinguishability classes than learning from answer sets, and anything that can be distinguished with those two frameworks can be distinguished with learning from answer sets. And then each of the extensions that we've done for ordering examples, for instance, and then for context-dependent examples, actually increase the one-to-one distinguishability class even further. So I've been calling this one-to-one distinguishability, and what I mean by this is that we're comparing one hypothesis to another and trying to distinguish a single hypothesis from another single hypothesis. It's also interesting to think about what happens when we're trying to distinguish one hypothesis from a set of other hypotheses. And the reason for this is that we might have a hypothesis space that contains many incorrect hypotheses and a single target solution. And so what we want to do is find enough examples such that our single hypothesis, our target solution, is distinguishable from all of the incorrect hypotheses in the space. If we do this, we get a similar result that both brave and cautious induction are strictly contained within learning from answer sets. So if we use this as a generality ordering, learning from answer sets is strictly more general than both brave and cautious induction. And again, the extensions that we've done to learning from answer sets with ordering examples and context-dependent examples increase this even further. We can also go even further and try to distinguish a set of hypotheses from another set of hypotheses, and this is known as many-to-many distinguishability, and again we get a similar generality ordering. So, given that we've shown that learning from answer sets is strictly more general than previous approaches, you might now be wondering, well, is there any price that we need to pay in terms of computational complexity? In fact, if we look at the complexity of two decision problems for logic-based machine learning, so that's verification, which is verifying that a given hypothesis is a solution of a task, so that it covers all of the examples of that task, and satisfiability, so that's deciding whether or not a given learning task has any solutions at all. The complexity of cautious induction in both cases is higher than that of brave induction, but the complexity of learning from answer sets and its extensions is identical to the complexity of cautious induction. So in the worst case, we don't actually pay any additional penalty when compared to cautious induction, even though we are strictly more general than cautious induction. The final extension that I want to cover in this tutorial is a notion of noise within logic-based machine learning. So everything that I've presented so far has assumed that all of the examples are perfectly labelled. Now obviously in the real world there's an unfortunate lack of perfection, meaning that some examples may not be perfectly labelled. These are what we refer to as noisy examples. So if we consider, for instance, we've got a learning task with a background knowledge that just says that we've got t of 1 to 10, we've got a single mode h that says that we're allowed to learn rules that define q. So effectively what this means is there's one rule in the hypothesis space, which is q of x if t of x, and we've got 9 positive examples for q and 1 negative example. Now, obviously there are no ways of covering all of those examples. So there's no hypothesis that proves q of 1 to 9 and doesn't prove q of 10 within the hypothesis space. But there is a hypothesis that covers all but one of the examples. So in the perfect setting that we have been discussing up until now, where all of the examples are perfectly labelled, the inductive logic programming system should return unsatisfiable, and so there's no solution that covers all of the examples. Whereas once you consider the fact that there might be noise within the examples, that's not really a sensible thing to do. What you should instead do is return the rule q of x if t of x, because it covers the majority of the examples. Another case where we might want to consider noise is where, for instance here, we've got a background knowledge where we've got t of 1 to 12, we've got f defining certain factors, so 2 to 4, and then we've got the multiple relation. So mul 2 will give 2, 4, 6, 8, and so on. Mul 3 will give 3, 6, 9, and so on, and similarly for mul 4. Now we're allowed to learn a definition of q, which says q of x if, and we've got some literals defined in terms of the multiple relation, where f has to be a constant, and we're allowed to use variables for t. Now say we've got q of 1 to 12 here, missing out the number 6, and we've got a negative example, q of 6, then there is a way of covering all of these examples, right? But it's very, very long. So the only solution is actually q of x if t of x and it's not a multiple of 2, So basically q of x if x is not a multiple of 2, q of x if x is not a multiple of 3, and q of x if x is a multiple of 4. Now, again, if the examples are perfectly labelled, then this is a reasonable thing to return, because it's the shortest solution that covers all of the given examples. But if the examples are not perfectly labelled, then is this really the right thing to return? Or rather, not if all of the examples aren't perfectly labelled, but if we're not sure whether the examples are perfectly labelled, it might be more likely than the fact that this complicated hypothesis is actually the ground truth. It might be more likely that we've simply mislabelled Q of 6, and instead that should have been given a positive example. So actually, it may make more sense, if we don't trust the example Q of 6, to just return Q of x if T of x in this case. The way that we represent noise within inductive logic programming, or the way that it's usually represented anyway, is that we give each example a weight, which is either a positive integer or infinity. So usually, when we're considering noisy examples, all of our examples will have a positive integer weight, and quite often this will be the same weight if we're just trying to maximize the number of examples that are covered, and we're not saying that any examples are more trustworthy than other examples. Sometimes, though, we might have examples from different sources, and so we might want to say that examples with a lower weight are more likely to be noisy than examples with a higher weight, because effectively what these weights mean is that we have to pay a penalty for not covering the example. So if we trust an example more, then we'll give it a higher weight, so that the penalty that we have to pay is higher. If we're sure that an example should be covered, then we can even give it an infinite weight. So this effectively turns it back into a non-noisy example, or an example that we know is not noisy. And it tells the inductive logic programming system that it has to cover this example. And then the formal definition of the task that we're trying to solve is, rather than trying to find a hypothesis that covers all of the examples, we're now trying to find a hypothesis that minimizes this scoring function, which is the length of the hypothesis plus the penalties of all of the uncovered examples. Inductive solutions must have a finite score, so this effectively means that they have to cover every example with an infinite penalty. And an optimal solution then is a solution with a score that is as low as possible. Now, there are some inductive logic programming systems that follow this approach that use a slightly different notion of scoring function, or even in the case of our recent FastLast system, allow the user to input their own scoring function, as this means that in a particular domain, if you've got a different definition of, say, the length of a hypothesis, or the function that you're trying to capture with respect to the noise, then you can actually inject this into FastLast and have it solve the task with your domain-dependent notion of scoring. The versions of ILASP that I showed you earlier in the tutorial do not perform well with noisy examples, or rather with large numbers of noisy examples. And the reason for this is that the iterative approach taken by ILASP2i to solve tasks with large numbers of examples doesn't work particularly well once you've got noisy examples. And that's because once you add an example to the set of relevant examples, usually this would mean that you have to cover the example. But once that example is noisy, it does not necessarily mean that the example has to be covered. And so what it means is that ILASP2i tends to have to add lots of examples that are, from roughly speaking, the same equivalence class before the penalty of those examples collectively makes it learn the correct hypothesis. And so it kind of undoes the principle behind ILASP2i. So we came up with a different version of ILASP. So this uses a notion of what's called conflict-driven inductive logic programming. And this is the basic principle behind both ILASP3 and ILASP4. There's some minor differences between the way that these components actually work in ILASP3 and ILASP4, but the high-level idea is pretty much the same. So the idea is that we take our task, and similarly to ILASP2i, we search for a hypothesis that covers everything that we've seen so far. And to start with, this is empty. We find a hypothesis. We then find a counterexample to that hypothesis. So this is the same as finding a relevant example in ILASP2I. But rather than then using that relevant example and adding it to a set of other relevant examples, what we do is called conflict analysis. So we try to take that counterexample and we compute what's called a coverage constraint from that example. Now, this is effectively a constraint on the hypothesis space. It'll say, in order to cover this example, you have to include at least one of the following rules, or you can't include any of these rules, or some combination of both. That's called a coverage constraint. We add that to our set of coverage constraints that works a little bit like the set of relevant examples, in that next time we get round to the hypothesis search, we're considering this extended set of coverage constraints and trying to find a hypothesis that satisfies them. Before doing that, though, we do what's called constraint propagation, and this is crucial for solving tasks with noise. So we take the coverage constraint that we've just computed and we try to work out which other examples are guaranteed not to be covered if we ignore this coverage constraint. So this means that once we've found a coverage constraint, even though it was found for a particular seed example, it won't just apply to that example. It means that we can say, if you ignore this coverage constraint, you have to pay the penalty not only of the example that it was computed for, but also of all of the other examples that we've propagated it to. And so it becomes a lot more powerful when we use it in the hypothesis search phase, because effectively we're boosting the penalty of each example. We then continue, find another hypothesis, and we keep going until we don't find any counterexamples that we weren't expecting. And when I say that we weren't expecting, now that we have noisy examples, it may be that this hypothesis search chooses not to cover certain examples. And so in addition to returning the hypothesis and the score, so the H and the S in this tuple, there's also a set of uncovered examples that we know not to be covered. So that's the set U here. And when we do the counterexample search, we're only looking for examples that are not in that set U. So examples that we were expecting to be covered that are in fact not covered. The first synthetic dataset that I want to show you is based on an agent planning problem. The idea here is that the agent is trying to get from one location in a grid to another location in a grid, but it is unaware of the rules that govern how it is allowed to move. So for instance, it doesn't know that in order to visit a locked cell, it must first visit the corresponding key. It's also not allowed to pass through walls, and it is allowed to use the linked cells to teleport from one location to another. The target rules are that something is a valid move if the agent can move to a particular cell from its current cell if the two cells are adjacent, the destination cell is unlocked, and there isn't a wall between it and the destination cell. Secondly, it is allowed to use the link cells to teleport from its current cell to the destination of the link, so long as that destination is unlocked. We can see this in action in the video here, where ILASP is going to, the agent underneath, this green agent that's moving through the cell, is using ILASP underneath to continually update its rules based on the observations that it sees. So you can see that as it gets more examples, it continues to add these and to rerun ILASP, so it's doing something similar to ILASP2I, and it is very quickly able to learn the correct solution. Next, I want to reconsider the journey preference example. So here we're trying to learn the preferences on the slide from examples of which journeys are preferred to other journeys, and we can give this with the ordering examples that I've shown you in the rest of the tutorial, where we just say that one journey is preferred to another journey. And you can see that is the red line on the slide, and even after only 40 examples, 40 randomly generated examples of those preferences, ILASP is averaging well over 85% accuracy. But if we increase the expressivity of the examples, and instead of just giving examples of which journey is preferred to other journeys, half of these examples now, so by the time we get up to 40, 20 of the examples are the examples that we've been given so far, so one journey is preferred to another journey, and the other half are journeys that are equally preferred. And actually, if we give half and half of these types of examples, then ILASP can learn even more accurately. So after 40 examples, it's averaging over 90% accuracy. If we look at the computation time of the systems that I've shown you so far, so this is a non-noisy learning task, so it's well suited for ILASP2I, we can see that ILASP2 very rapidly shoots up with respect to the number of examples. So you can see it goes off the scale after just over 100 examples, whereas ILASP2I is increasing much more linearly. So you can see even after only 500 examples, it's taking less than 20 seconds to solve the learning task. And you can see that the memory usage is much lower correspondingly as well. The middle line, the green line, is on a slightly modified version of the system that uses ILASP2I's iterative approach, but doesn't take advantage of context-dependent ordering examples. So it doesn't take advantage of the fact that the examples are context dependent. And so we can see here that actually the speed up between ILASP2, which is also not able to take advantage of the context dependent representation of the problem, and ILASP2I, there's kind of a middle ground where we use the iterative approach of ILASP2I, but we don't get any advantage from context dependent examples. And we can see that the benefit of both is roughly equal. So it's sort of half of the benefit for the context-dependent examples, and then the same again for this iterative approach that ILASP2I takes. The last synthetic dataset that I want to consider is the dataset concerning Hamilton graphs. So here we have injected some noise into the problem, and in the graph below you can see that it ranges from 0 examples up to 200 examples. And what we've done is taken 5, 10 and 20% of these examples on the red, green and blue curves respectively, and flipped the label from positive to negative or from negative to positive. We then tested the hypothesis that ILASP learned on a further 1,000 graphs, and you can see the average accuracy plotted against the number of examples. And what's interesting here is that although even with 20% noise, ILASP is able to learn accurately after only around about 160 examples, it takes ILASP longer to learn accurately, or rather more examples to learn accurately, when there's a higher proportion of noise. And this makes sense. So the more noise there is in a problem, the more data you need in order to work out which of the examples are noisy and which of the examples are truly showing the pattern that you're trying to learn. The other thing that happens as you inject more noise into the problem is that ILASP tends to require a larger number of iterations, and so you can see that the running time actually increases faster when we have more noise in the problem. But still, even with around 200 examples, ILASP is able to solve the learning task in an average of around 4 minutes. Finally, I'm going to show you a couple of real data sets where we've applied the ILASP system. So the first is on a sentence chunking dataset. This has previously been used to evaluate the INSPIRE system for Brave induction. So INSPIRE was evaluated on a dataset of sentences that are chunked into their various parts. So for instance, Thai opposition party to boycott general election should be split into Thai opposition party to boycott and general election. There are two versions of this dataset, one with 100 examples and another with 500 examples, and there are 5 categories of sentences for each of these two versions of the dataset. And you can see that in each case, ILASP is actually learning with a higher F1 score than Inspire. Now, the reason for this is that ILASP is guaranteed to find an optimal solution to the task, whereas Inspire takes a few shortcuts along the way. That means that although it has a similar notion of penalties for examples, it doesn't guarantee finding the global optimal solution. And what this means is that because ILASP is finding the optimal, it ends up being a better quality hypothesis when it's evaluated on the test data. Nonetheless, although ILASP is solving a harder task in finding the optimal solution rather than just approximating it, it is able to solve both versions of the task, so the 100 examples and the 500 examples versions, in less than half an hour per learning task. Whereas in the Inspire system, it had to have a timeout of half an hour for one of the parts of its algorithm. So ILASP is actually, in at least some cases, is faster than Inspire, and it is finding an optimal solution to the task. The other interesting thing to point out is that whereas Inspire in 4 out of the 5 cases gets a higher F1 score on the version of the dataset with 100 examples, the converse is true for ILASP. So ILASP is actually, in 4 out of the 5 cases, finding a hypothesis with a higher F1 score, on average anyway, in 4 out of the 5 cases for the tasks with 500 examples, which means that with more data, ILASP is performing better. And that's what you would expect. We suspect that the reason that Inspire does not perform better with more data is that its approximation actually becomes worse as it gets more data. So the timeout effectively is kicking in earlier in the optimization process because it's got more data, so it doesn't get as far in the half an hour that it's got. The second real dataset that I want to talk about is the Caviar dataset. So this has also been used to evaluate other ILP systems in the past, in particular the ILED and OLED systems. This dataset consists of a set of videos of people meeting and fighting and performing other actions. And the task is to try to learn the initiating and terminating conditions for various events. So the version that I'm about to show you is just on whether two people are meeting. So we're trying to learn the definition of what it means for a meeting to start, so the initiating condition, and the definition of what it means for a meeting to end. So we can see this in the demo here. This is a video clip showing two people meeting. A third person is walking past, and you can see that the meetings are only between the purple and the pink labelled people. There's no meeting taking place with the third blue labelled person. There are lots of clips of this form in the Caviar dataset. We can select a training set from this and generate the learning task. In this case, I'm just going to give all of the examples so that ILASP has as much data as possible to learn from. I'll generate the learning task. And we can see now this has generated an ILASP task with lots of different examples, one example per pair of frames. I'm then going to start the learning, and what you're going to see is an iterative representation of ILASP's conflict-driven ILP procedure. So you can see here the error against what ILASP thought the penalty of a hypothesis should be compared to what the penalty actually ends up being. So you can see the actual score, the expected score, and then the error is the difference. And you can see early on this is high and there are quite a few spikes, but as ILASP computes more and more coverage constraints for the different examples, you'll see that this error starts to come down. So it's not monotonic, there will be a few more spikes, but as it performs more and more iterations, you'll see that it will converge on 0. And as that happens, the hypothesis converges on something that makes a little bit more sense. So for instance here, these rules are being automatically translated, by the way, from the ASP representation. The top one says that two people stop meeting if one disappears from the frame. Ironically, that rule has just disappeared from the slide. So this will keep going until until it converges to 0, at which point the set of rules correspond to the optimal inductive solution of the task, and that is what's just happened. So you can see after around 42 or 41 iterations, ILASP4, this is actually, has found the optimal solution of the task. Now, because these rules are encoded in ASP, similarly to other ILP approaches, these rules can be automatically translated into plain English, meaning that this is an inherently explainable form of machine learning. So if you've got to the end of this tutorial, thank you very much for listening. Before you go, just a bit of shameless advertising. The ILASP system that you've seen in this tutorial is available to download, and if you get in contact with me at mark@ilasp.com, I'm always happy to help new users of ILASP, especially when they have interesting applications. If you're interested in following our latest updates, you can do that on the social media links on the slide. Thank you very much.